Hi everyone, welcome to the Earth Science Regents Review podcast series created by the Hommocks Middle School Earth Science Department. Today we're going to be talking about the layers of the Earth. Now here's the problem with this topic. We actually haven't gotten past 7.5 miles into the Earth. So the other layers, the mantle, the outer core, and the inner core, we don't really know that much about because we physically haven't been there. So we've had to make inferences, lots of inferences, regarding these subsequent layers. So where do our inferences come from? Our inferences come through the study of seismic waves, specifically S waves. We'll get into a little bit more detail about the relationship between S waves and the outer core. Study of meteorites, in terms of what meteorites are made up of compared to what the inside of our Earth is made up of. We'll talk about that relationship as well. And volcanoes. Because volcanoes are the vents on the planet, they spew out rock, they spew out lava, they spew out lots of gases. Seismologists can take the material that comes out of volcanoes and they can kind of piece together a picture what maybe the inside of the Earth might look like and what the inside of the Earth is made up of. Now, we have an idea that the Earth has different layers within different depths. So what we're going to do is we're going to talk about the different layers now. The outside layer is what we call the lithosphere. Now, the lithosphere is going to be made up of two layers within the Earth, the crust and the rigid mantle. The crust and the rigid mantle together are going to make up the lithosphere. What's going to be important about this is that the crust and the rigid mantle together, the lithosphere, is probably the most widely studied section of the Earth because we can get to it. It's very easy for us to drill into because we live on it. It's the outside portion of the Earth. Now, there's two different parts of lithosphere. There's two different parts of crust. We have oceanic and continental. Oceanic crust is made up of basalt. It's a little bit thinner. Continental crust made up of granite. It's a little bit thicker. Thicker, very simply because there's more mountain ranges on the continents. There's also a density difference as well. Continental crust is a little bit less dense. Oceanic crust is a little bit more dense. That's going to be important when we start talking about plate tectonics next chapter. The MOHO is a boundary between the crust and the rigid mantle. Well, what separates the two layers? Density. Through the study of P waves and S waves, we have been able to discover that when earthquake waves exit the crust and enter the rigid mantle, not only do they speed up, but they also bend. Fancy word for bending is what we call refraction, and that's all caused by a density difference. That boundary between the crust and the rigid mantle is what we call the MOHO. The next layer is called the mantle. There's actually a couple parts of the mantle. We've already talked about the rigid mantle, which is part of the lithosphere. Next off, we're going to talk about a section called the asthenosphere. Now, this is a very important layer in regards to plate tectonics, which we'll get into a lot more detail later on in the school year. But scientists believe it's almost silly putty-like or clay-like in the sense that it's going to move, it's going to flow like a fluid, but it's still solid. Think about a piece of clay or a piece of silly putty. You can move it, you can mold it, you can manipulate it, but it's still going to be solid. So scientists call it the plastic-like mantle. A heat transfer called convection takes place there. And we'll get into a lot more detail about convection later on in the school year. It's the upper part of what we call the stiffer mantle. Now you can see the diagram here shows you the convection going on. Again, we'll explain this in a lot more detail later on in the school year. The stiffer mantle is going to be important because it's our largest section of the Earth. It takes up about 80% of the Earth's volume on the interior. So it's a very, very big section. The outer core is very important because what happens here is through the study of S-wave travel, we believe that the outer core is liquid, very simply because S-waves cannot pass through this outer core. What happens is they get absorbed, and you get what's called an S-wave shadow zone on the opposite side of the earthquake focus. So we believe that even though we haven't been to the outer core, we believe that the outer core is liquid very simply because S-waves get absorbed into it. They can't pass through it. We also make the assumption and make the inference that it's made up of iron and nickel in the liquid form. The outer core just has not had a chance to cool off and turn solid, so it's still believed to be liquid at this time. You go a little bit deeper into the planet, you get to the inner core. Now, the inner core is believed to be solid, very simply because that the pressure is so immense at the center of our planet, it just will not allow the molecules to go from solid to liquid, will not allow it to melt. So that outer inner core is strictly solid. Again, through the study of meteorites, we believe instead of being liquid iron and nickel like the outer core, it's solid iron and nickel. So those are your basic layers within our planet. Now, there are some relationships as you increase your depth. As you go deeper and deeper into the planet, your temperature goes up, your pressure goes up, and your density goes up. Those are all direct relationships. It's very important to know page 10 in your Earth Science reference table. That is going to be the inferred properties of the Earth's interior chart. Please make sure you know how to use that. So that's it for now. We'll talk to you soon. Bye-bye.